Hello guys, let's continue with our erratic motion. It's still part of the rectilinear motion. I remember the last time we talked about the position time graph and also the reason why we are using graphs to show the motion, because in this case the motion is changing, so we need to define it in certain time intervals, and then from there if we can get the formula for different time intervals, then we can either derivate them to get other relationships, or we can take an integral to get other relationships, right? But in this case, we'll look at the fact that, let's say now you're given the acceleration time graph, right? All right. So this is our acceleration time graph. Remember something about the acceleration time graph, that it comes from, so your A is equals to dv dt. These are our formulas. So your V equals to ds dt. And then we have the last one, which is ADS equals to VdV, right? So if you note these things, if I'm given an acceleration time graph, in this case, I can get my velocity here by saying, therefore, your dv equals to a dt, solving the first equation here. And then that means here, if I take the integral on both sides here, provided I have my initial conditions like t naught and then also v naught here, then I can, so that's going to be v and then that's going to be t, right? Then I can get the integration, then I can get the equation of my velocity for that certain time interval from t naught, let's say from t naught to t1, right, to v1 as well. And then from there, now I can do this for small time intervals, and then I add them all up. Then those series of functions gives me my velocity time graph for the whole function, right? So let's do that. Okay, remember those equations. I think I should just put them up here. Acceleration time graph, that is fine. You're gonna have something of this nature. Let's assume this is your graph here. Alright, so let's assume this is the graph of your acceleration. It starts somewhere here, right? So what you can do here, we do the very same thing here, because we need, so we need it, we given acceleration, we need position and velocity to define our kinematics for this path, right? So here, remember, this is acceleration, meters per second squared, and here you get time in seconds, right? Then in this case, I can divide this thing into time intervals, right? Different times. So the more partitions, remember, the more accurate the results are going to be. So if you still remember the area method, because your velocity is just the area under the curve of acceleration, remember that. So integrations, they were derived from the area problem. So if you still remember that, I can say here, I will just write it up here. So area of this graph, area of A of t equals to V of t, right? So area under this curve here is going to give you the velocity time graph. And then you know that how do you get your area? You can use the integrals, right? So if you still remember the fundamental theorems of calculus. So let's see here. We got that. So here, these are our points here. We can divide this thing into V1, V2, and V3. So if I take the area here, the first region, this one, so this area is going to give me my first velocity, right? And how do I get that area? First of all, we're going to say the time starts at t naught, but then this part is at t1, right? So I want my velocity. So this is here a naught, right? So I can get my velocity from that equation. Remember, I said that dv equals to integral of a dt. This comes from our equation a is equals to dv dt, right? Then in this case, let's put our the integral of that is equals to integral of that. So let's put in our boundaries. So this is going to start at t naught, then it's going to go to t1. This one is going to start at v naught, and it's going to go to v1, right? And then let us agree what I'm going to get here is v1 minus v naught, right, which is just change in velocity. This is equals to, then if I have that change in velocity, I can just say it is equals to that integral from t naught to t1 a dt. But please note one thing now. The change in velocity, it means that now from v1 to v0, this is the change in velocity. So therefore my v1 itself is just going to be equals to this, the change in velocity, which is this whole thing here, plus the initial velocity, right, v0, right? So please note that. So it's the same thing as just breaking this thing into v1 minus v0, and then I take v0 on the other side. So this is going to be my v0 here. So my v1 is equal to change in velocity plus v0. Then this is how you will get your successive points here, right? Then for your v2, you know that also I can just say here vn equals to delta v plus v0, right? But the best way I would say it's vn minus 1, right? So that you take the previous velocity for your area. Right, so that's just the case here. So for v1 you can take v0, but for v2 you can take v1 and v2. That should be fine as well. Doesn't really matter, because I don't want you to take v2 and v0. That gives it a, so if maybe I would come here, now it means that you are taking this whole area. If you're gonna use t2, which is here, and t1, then there's so much time that has elapsed, and the motion has changed. You will get so much inaccurate results, because there's so much time in between the two time periods that you're comparing, right? So that's just the case here. As long as you know that this is how you get your velocity from the acceleration time graph, you take the integral of that equation. Then from here, let me try to plot those points so that you can see how it's going to look. So for your velocity time graph, so now it's going to look something of this nature. So here you still got your time in seconds, and then here you have your velocity in meters per second, right? So what happens is I can do the same partitions here. This is still my t0, t1, t2, then t3, and so on, right? Then these partitions, I come back there and I look for those values. So remember I said my v1 is equals to this, and then my v2 is going to be changing v plus v1, right? So let's try to do that. Initially our, okay, it's fine, we will put the initial velocity here. Doesn't really matter what your initial velocity value is, but your graph is going to start there at the initial velocity, right? And then from there, your curve, you can continue with your curve now, using those areas. So probably, or this might be something of this nature, doesn't really matter. And let's say if that one looks like, okay, if we can say maybe that was quadratic, this would look something more like a straight line, right? If you have a quadratic one, you're gonna get a straight line for this graph here. I don't know if I want to draw it. Let us assume that was it, because remember something, your integration, it increases your, sorry, this is not supposed to be a straight line, I'm making a mistake. If that was a straight line, this was going to be parabolic, but then now if this is parabolic, then this one right here has to be cubic, because remember your integral always increases the power. So if I have an integral of x, this is going to be of x to the power of n is going to be x to the power of n plus 1 divided by n plus 1. But what you see here is that the power of x goes up, meaning that if now my acceleration was linear and I take an integral of a linear graph, I'm going to get a parabolic for the velocity time graph. But then in this case, if it is parabolic, then I'm going to get a cubic graph here, right, which is x to the power of 3. But then if that one was x to the power of 3, then this is x to the power of 4. So that's just the case here. Just know that going from acceleration to velocity, we go up, the degree goes up by 1. Also, when you go from velocity to position function, then your degree goes up by 1. But then now it's the other way around. When you come from position to velocity, then the degree goes down by 1, because we are taking a derivative, and your derivative reduces the degree of your variable, right? So please note those things. Okay, cool. So let's try to draw this curve here. So I'm just gonna random. Okay, I don't want it to look exactly like that one. Just maybe something. Okay, I'm not sure if I'm gonna try something like that. I think it's fine like that. So that at least is different, and then you can do the same partitions. Then now here you do know that these are going to be your velocities, your v1s and v. So this is your v1, v2, you got your v3, you got your v4, and you get your v5. And remember, how do you get all these v's? We are using this equation right here, right? And then this means now here, if I'm finding the difference between two velocities, like between v0 and v1, so if I were to trace it here, it's gonna be somewhere here, right? But now the height difference, which is a very small height difference there, is gonna give you your delta v, right? This is the height difference from v0 to this one. Also, you can get this height difference if you want to see it clearly also here. I'm going to try to show it here with a different color. If you go from v3 to v4, this is the height difference, right? So this is where they meet. So this right here is your height difference. Then that part right there is going to be your delta v, right? And this is how you would draw these successive points. You get each point by saying that v1 is equal to delta v by v0, v2 is equal to delta v plus v1, right? So your delta v, it is going to depend on the equation that you're going to get here. And your delta v changes because remember, we do not have a continuous motion. So your delta v will change depending on the part of the motion that we are at, right? And then also this thing that I'm saying, that if this is parabolic, I'm not meaning that the whole path is parabolic, right? If there's a part here which is parabolic, and then we are given an equation, because remember also, to construct an acceleration time graph, we need a series of functions, because this is a changing motion. So each time interval is defined by a certain different equation, right? So when you take the integrals of those equations, you are getting your velocity, right? Even though here now we are using it as mostly we are just looking at one time interval, and then you know that your change in v is going to be that. Keep that in mind, that it's a series of functions, it's not just one function here. Okay, now that you know the velocity time graph, how can you get the position time graph? So now we already know what is the change. So CT graph, position time graph. In this case, it's the same thing, because remember your position, which is the integral of ds, is just going to be equal to the integral of dv dt, sorry, of v dt. And then this is going to start from t naught, because the differential is time, to t1, and then here I'm going to start s naught to s1. So remember that. And then this comes from the equation that you know that your velocity is equal to ds dt. When you solve for ds, that is just going to be that integral there. All right. Okay, let's draw this graph as well. It's going to look something of this nature, whereby you will have the same things here. So it's the position in meters, and then this is your time in seconds. And then now let us try to get that one. It's probably gonna look something of this nature. Just gonna I'm doing something out of my head here. It doesn't really matter. Not really a straight line. I don't want it to be a spoiler. Yeah, let's assume this is the graph you're gonna get from that velocity time graph, right? But what I want you to track is the position. So here you have your S naught, and then here at this point at T1 you're gonna get your S1. That is going to be that point. So we plot all these points here, your S2s, your S3s, your S4s, and then your S5s. So you keep on plotting all of them, right? So here you have your S2, then here you got your S3, and so on, right? So when you plot them, this is what you're gonna get. But S1, you know, it is just going to be the area under the velocity time graph. So your S1 equals to delta S plus 1, and your delta S here, it is just this difference here, right? So from S2 to S1, that is your delta S. It's just the height difference here. So you're gonna get that, and your delta S is this thing here, remember, because delta S equals to integral from of v dt from t0 to t1, right? So that is just the case there. This is how you would do your graphs. So you do this for all those series of functions. So if maybe velocity time graph was given by 5 series of functions, so also here you will do this integral for those 5 series of functions, and then you can plot your position time graph, right? But yeah, that is just the case here. This is your erratic motion position time graph, going from acceleration time graph to position time graph. The last time we went from position time graph to acceleration time graph. Now we're gonna look at the relationship between acceleration and position and velocity and position, right? But let's end this one here. Thank you.